Okay, hello everyone. So this is the first lesson, first discussion for this semester. Our topic is electric charge. So this course is the second part of the physics you took in fall. Here we'll be talking about electricity and magnetism. Those are the two main categories, and there's a couple of subtopics inside. As I said, the first topic is electric charge. So these are some of the topics inside that we'll be discussing: static electricity, charge and conservation, electric charge in an atom, and there's induced charge, and then Coulomb's law. So we'll be solving some mathematical problems under Coulomb's law. So you'll notice that I'm making these videos a little different compared to the last semester. Last time I didn't have the PowerPoint slides included. They were kept separately, but then I thought it'll be more convenient and more useful to you if I put the PowerPoint in the video. That way you can see better diagrams rather than me drawing the diagrams on the whiteboard. So PowerPoints will be here, and these slides are from a different textbook. It's not the book I'm recommending for the course. This is slightly an older textbook. It's called the Giancoli physics textbook, but the topics are same. Subject matter is also same. Your textbook has a little bit more information, newer information, and with more details, with better diagrams, but other than that, physics is same regardless. Okay, so let's start. So these are the topics we'll be discussing, and let's go step by step. Let's see. So we're gonna start with electric charge. Now you might have like a brief idea what electric charge means. Your cell phone has a battery, right? And then when it runs out of charge, you have to recharge it. So you're putting something in it using electricity. You're recharging, you're adding charges to the battery, which is needed to operate the cell phone, the mobile phone. The car battery, right? It has the motor vehicle has a battery, and it has charges which is needed to operate the car, to operate the engine. And once in a while, maybe once every few years, the battery drains, and then you have to get it recharged, or you have to get it replaced. So there is something called charge that is there, that are useful, that are needed for electrical functions. So that's what we're going to talk about. Another familiar example, especially in the winter time, you get these little static electrical shocks, right? Like when you touch a doorknob, there's a little spark going between your fingertips and the doorknob. So there is some kind of electricity going back and forth. That involves something called the charge. So that's what we're going to briefly discuss. Okay. So what is charge? What kind of, is it matter? Is it energy? What are the properties? So electric charge is a fundamental property of nature. It's a basic property, right? And we say that there are two types. There's positive charges, right? There are negative charges. What are the examples? So two types of charges, right? Charge can be divided into two types: positive and negative. Examples, you might have heard of these terms before. Positive charge, a simple example is a proton. Proton is a small, tiny particle. Atoms have protons in them. There's other different types: protons, electrons, neutrons. So proton contains this fundamental property called the positive charge. So a proton has certain characteristics, certain behavior. By looking at that, we assign this property to it. We say that it has a positive charge. It has other things like its mass, its spin, and all sort of things. Charge is one of those characteristics. So a good example for a positive charge is a proton. Negative charge, the opposite type. An example is an electron. Usually in physics and also in chemistry, we use the symbol little p for a proton and little e for an electron. So how much charge? So how do you measure charge? That we will come to that in a minute. The unit of charge, how to measure it. So for the time being, have the idea that there is a fundamental property in nature that is called charge, and there are some examples you can give, like for positive, you can say protons or couple of protons in a molecule. If there's a bunch of protons, that's a positively charged molecule. And an example for negative charge is an electron. These things have freedom to move, they interact with each other. So there's so many interesting things we can talk about. So let's start with how to add or remove charge into an object, how to make an object charge. So as you see in this slide, objects can be charged by rubbing. So the diagram, you see that a person has a wooden ruler, like a meter stick kind of thing, a wooden ruler in hand, and then he's rubbing it with a piece of cloth. So this is something you can try at home. Take a piece of wood, or it can be a piece of plastic like a pen or a pencil. Rub it against a piece of dry cloth vigorously for like a minute or so, and then before doing that, have some little pieces of paper. Like take a piece of paper, cut it into tiny little pieces. They have to be really small, like the size of like a grain of salt or sugar. Small pieces. And then take this pencil, the wooden pencil or the plastic pen, rub it against a piece of cloth. They have to be dry, or you can rub it against your hair. That also works. And then slowly bring that thing close to those pieces of paper as shown in the diagram, and you see something going on. Things are moving. So this is a very simple but interesting way of showing how charge works. So we'll get to the explanation in a little bit, and let's see what else we have in these slides. So here we're going to talk about another property of the charge. So the slide, it says charge comes in two types, positive and negative, and it says like charges repel and opposite charges attract. What does that mean? Here in the diagram you see that there's two plastic rulers. The first one, the one on the left hand side is hanging by a thread, and it's negatively charged. So here we have the ruler. It's like this. Negative sign says that it's negatively charged, and then you are bringing another negatively charged ruler. You are bringing this in, so you are holding it with your hand. So these are like charges, right? They both are negatively charged. This one is to free, this one is hanging by this thread, so it's free to rotate. So when you bring the second equal charge close to this one, it's gonna move away. Second diagram shows the same thing. This time we have positively charged ruler, and you're bringing another positively charged object. It's gonna repel. It's gonna push the other guy away. Equal charges, they repel. But if you bring, here's the negative one, if you bring a positively charged object, opposite charges, there's attraction. You can show the same thing using electrons and protons. So here we have a proton. It's a tiny little spherical like object. That's how we indicate that a proton in a diagram. Really the dimensions are so small, we can't see a proton with our naked eyes. As a matter of fact, even the strongest microscopes won't be able to see these particles, these actual particles. You need like very high resolution electron microscope, kind of have to go to like that level at least to see signs of these individual particles. Okay, so let's say you have a proton. Just assume that there's a proton and you bring a second proton close to it. They're both positive, so the force between them, there's a repulsion. The way we indicate that is they're pushing away each other. So the force on this one, let's say proton 1 and proton 2, proton 2 is pushing proton 1 away. So we can say F12, force on 1 due to 2. It's away from the second one. Same thing here. F21, force on 2 due to 1 is again away from the first proton. Equal charges repel each other. We put two electrons, so electron and another electron pushes each other away. If we have a proton and an electron, opposite charges, this is positive, this is negative, there is attraction. The force is going to be towards each other, right? Okay, so let's move on and see what we have next. Electric charge is conserved. The word conserved, right? The total number, the arithmetic sum or the mathematical sum of the total charge does not change in an interaction. What does that mean? So for an example, let's say you have a charged object, say a bunch of negative charges, and here's another object that is neutral. There are no charges. You bring this first one closer to the second one, you kind of place it on top of it. So there could be like a little charge exchange. This highly negatively charged object might lose some charges, and this uncharged object might receive some charges. When you add up the totals, like whatever the charges here plus the charges here should be the total that were originally in the first object. The idea is you can't destroy, you can't create charges. The total number is always going to be the same, right? They can move between objects, they can leak to the outside, but once you add up everything, when you include everything, the total is equals to the original total. All we can do is move them from one place to the other. You can't create them. Whatever created at the beginning of the universe, it's the same number, right? So there's more information. You please go to the textbook, read these relevant pages, go to the relevant chapters. There's so much interesting information. Even when you produce charges in the laboratory, like let's say you try to produce a negative charge out of like that didn't exist before. So if you produce one, at the same time an opposite charge also get created, so the total remains the same again, right? Okay, so let's see what's next. Electric charge in the atom. Now you all familiar with atoms, molecules, ions, those kind of key terms. I believe you guys have taken chemistry introductory classes, so these things are discussed. So again, atom is like the smallest building block of matter, right? In very simple terms, we explain the atomic structure as a positively charged center, the middle part, with negatively charged electrons moving around it. So here you see in the diagram, the middle part, we call it the nucleus of the atom. Small, massive positive charges, so there's positive charges. There's neutrons also in the nucleus, which doesn't have neutrons. No charge. Neutral particles. And there's protons, which are positive charges. So the nucleus is dense, very highly compact. These positive charges in the nucleus, so one can ask the question, if positive repel, how come nucleus is stable? Because all these electrons want to get out of it, right? Because they are repelling each other. So this is a different branch in physics. Under nuclear physics, we talk about this strange force where the neutrons, these people without any charge, they somehow manage to keep everything intact. There are other forces in nature. We talk about electric force. That's this chapter. There's gravity. It's another force in nature. We talk about gravity briefly. In the last semester, we talked about gravitational attraction, all that calculations we did. Gravity is another force in nature. And there are two other forces that scientists have identified. Strong force and weak force. Some weird names they have given, strong and weak force. These are nuclear forces. They exist inside the nucleus, inside the atom. You won't see these things outside the atom like in our day-to-day life, right? These are very specific, short-range, micro-level forces. So these strong and weak forces, especially the strong force, is what keep the nucleus in place, pulling against the electric force between protons. So that's the duty of neutrons. So anyways, let's get back to the topic. So you have the nucleus in the middle, positives and these neutrons, and you have these electrons going in different orbits, right? And in chemistry you learn that the first orbit can have 2 electrons, the second one, as I remember, 8, and then another 8, something like that. That's we say the classical explanation of the atom. The modern explanation, the quantum explanation, is a little different. We don't assign specific orbits. We talk about the probability, the highest probability of finding the electron at some distance, and we call that's the orbit, right? So it's kind of a fuzzy explanation. Anyways, this is the atomic structure, nucleus in the middle and negatively charged protons around it. And then there's this attraction between these opposite charges, keeps these electrons in place, preventing them from going away from the atom, right? Okay, here's another example. So here you see the familiar H2O molecule, or the water molecule. Now you see that due to the particular structure, you have the oxygen here and then the 2 hydrogens connected to that, And in the water molecule, it's a very unique molecule. I mean, water is all around us, but so unique at the same time. There's a charge separation. The oxygen has more negative on one side. The hydrogens being the proton. Like, what is hydrogen? Hydrogen is a proton. Nucleus has only one proton. That's all in the nucleus, and there's one electron around it, right? So overall we have, and then even though I draw this electron over here, it's all around the proton, like an electron cloud with one single electron. So overall, this positively charged proton and the negatively charged electron cancel out the total charge, makes it zero in a very symmetric way. But compared to that, it comes to the H2O molecule, the water molecule. Because of this particular shape, because of this bend here, the molecule has a more negative end and a more positive end, right? So that molecules like this, we call them polar molecules. They're polarized. Charge is not evenly distributed. That is a very significant thing that gives all these unique properties of water. It's being a liquid, you know, ice, when it freezes, when it becomes ice, it's less denser than the liquid, which is really unique. Like in many materials, the solid form is more denser than the liquid form, but for water it's opposite. Ice floats on water, and that is really important to the life on Earth. So there's so many interesting things comes with this particular shape and this charge distribution, charge separation, being a polar molecule. Alright, so let's see what's next. Insulators and conductors. So let's talk about another property of charges. So so we can characterize materials based on how they allow charge to move inside them. Insulators and conductors. So conductor. So let's say some material, a piece of iron. There's iron molecules. So here's the iron atoms, the nucleus. So this is a piece of iron we are talking about, right? And then there's electrons around them. These electrons belong to these atoms, but it's a property of iron and a lot of other metals that they have the bigger atoms, means they have more protons and electrons, like compared to hydrogen, one proton, one electron. Iron, I believe the atomic number is 56 or something like that. I'm not sure. You can easily check on your periodic table. There's a lot more electrons and protons, and inside the structure this attraction is for these outer electrons, it's very weak. So these electrons are free to move around. They have much more freedom. These kind of materials are called conductors. Charge flows freely. These electrons, these charges can flow freely. Remember, in this case, not the nucleus, right? The nucleus, the heavy, massive part, doesn't have much freedom to move around. Electrons, they can do move around a lot. So these kind of things are called conductors. Another important thing to remember, okay, we'll come to that in a minute. The counterpart is insulators. A good example is a piece of wood, right? Hydrocarbons, mostly hydrogen, carbon, oxygen, and nitrogen kind of stuff. The particular bond between these atoms, hydrogen, carbon, oxygen, they don't allow electrons that much freedom. They're tightly, like, they're very confined, right? Strong attractions. So the electrons do not have much freedoms to move, almost no charge flow. So we say these kind of things, insulators. Another important thing, electrical conductors are good heat conductors as well. Electrical insulators are good heat insulators as well. Electricity conducts by the flow of charges. For heat conduction also, you need some kind of charged particle, some particle with freedom to move around. So in conductors, electrons have that ability to move around, so they can conduct heat well. When it comes to insulators, electrons, protons, everything have fixed locations, no much freedom to move around, cannot conduct heat as well. And there are a third type in between materials. We call them semiconductors or semiconductors. So that's a field by itself. The entire Silicon Valley runs on semiconductors. So sometime later we will get to that. But again, in your textbook, there are some good information about them. If you look at the diagram here, you see that there's a charged sphere, positively charged, and there's a neutral sphere. You place a piece of metal, in this case a metal nail, an iron nail. So the charge get distributed because they jumped onto, in this case we can say, we know that positive charge is not going to move, only the negative charges move, but for the sake of explaining this, you can think of a couple of positive charges go through the nail, comes to the other side. You try to do the same thing with a piece of wood, nothing will happen because wood is an insulator. Okay, so finally let's talk about a little instrument that we use in labs, physics labs, to identify, to indicate charge. Now it is called electroscope. So we talk about conduction, motion of charges. We talk about inducing charges. So remember the very first, one of the first examples where you have a piece of plastic and then you rub it with a piece of cloth and this will charge this object. So what really happened here is, so this is the piece of cloth, right? This is the plastic or the pencil or the wood. When you rub one object against the other, due to their chemical properties, now this thing has some atoms inside, some molecules. The cloth has some atoms, and they all have their own atomic attractions. It's all based on how strong these attractions are. Sometimes one can attract electrons from the other. Let's say the atoms in the cloth are able to attract electrons from the plastic. So what happens is, electrons are moving from here. So you're losing negative charges, right? The plastic is losing negative charges. It's losing negative charges means the plastic gonna become positively charged. Piece of cloth will become negatively charged. This is charge by friction, or we can say charge by induction also. You are inducing charges, you are moving one to the other. So once you have that charged object, just give me a second. Okay, so here we are charging an object by friction. So that's one way of charging things. The other method as we saw in the previous slide, so if I go back, let's see, here we have a charge object, this sphere, and we have a neutral object. You put a conducting some conductor between them. Here we are charging the second one by conduction, right? So you conduct charges from one to the other, so you charge the second one. So that's another way of charging things. There's a third method, so let's see. Over here, so here again, charging by conduction. So you have this okay, let me come to that in a minute. All right, let's go back. Let's say you have this positively charged object and you have this neutral object, right? And then you bring this positive object close to the neutral one. So what happens is, once you are really close, all these positives, so the neutral object, the atoms inside, they feel the presence of these positive charges. So we know that like charges repel, opposite charges attract. So more electrons, if this is like a metal object that has freedom for conduction, more electrons will gather on this side. The positives will be here because they don't have much freedom to move, but there will be few negatives here, but most of the negative charges will get attracted to the left side. There's no physical contact between them, it's just near to the object, but it's not really touching the object, right? So here what we have for this object, the second object, you have a more negative left side and a more positive right side, relatively positive. This is charging by induction. No physical contact. This can be a temporary thing. Once you get rid of this guy, charges can go back to where they were, but temporarily you can charge. It's common to conductors. It can happen in non-conductors as well. That's what the diagram shows. This is what happened. Remember, the one of the first things we discussed, like you bring this pencil close to pieces of tiny little pieces of paper. This is charge, let's say positively charged. It creates a temporary charge separation from this little particles, little pieces, as shown in the diagram, and that temporary charge separation can create attractive forces. So these are things I want you to read, do your self study, get a better idea. You can Google this. I mean, YouTube has ton of explanations. Your textbook has nice explanations, so read those. And so let's move on and see what is this electroscope looks like. So it's like a metal casing. There's a glass window so you can see what's going on. There's a metal tip, and it's the other end of it is attached to these very thin gold leaves, right? So these are metal leaves, very light, very less weight, and they have the freedom to move back and forth, and it's covered in a glass casing, so you know the outside like a wind or breeze, it's not going to affect this, and you can see what's going on. So then what you do is, let's say initially the electroscope is neutral, there is no charge. Then you bring this positively charged object near to the electroscope. So it's gonna pull all the electrons closer to the tip, making the other end relatively positive, right? Because the bottom side is losing electrons. Electrons are moving to the top. Now we have a charge separation. Now the leaves have more positive in them, so the leaves gonna go away from each other. So for an example, so here's the two leaves. Bad diagram, sorry about that. Initially neutral, but when they become positive, they're gonna move away from each other because they're positive. These are the leaves kind of moving away from each other. So we can use an electroscope to see whether something is charged or not. You bring this unknown object close to the electroscope. If the leaves are moving away from each other, that means there is some charge. We can't say for sure whether it's negative or positive. It acts the same way for both charges, but we can say for sure there is something, there is some charge. And let's say you actually make the physical contact, like in the second diagram. The charged object touched the electroscope. So some of these negatives will leave the electroscope and jump to this incoming pink color object. So the electroscope is going to permanently lose charges. Now you have a permanently charged electroscope. This thing can hold this permanent charge for a considerable time, sometimes a couple of minutes at least. So the leaves will remain apart for a longer time. Now let's say you do the opposite, right? I mean, these are a bunch of other examples, like you charge it negatively and then you bring a negatively charged object. The leaves gonna move even further apart. You bring a positive one, it's gonna bring all the positive to one side. The leaves will come closer to each other. So an electroscope can be used to identify. This is a very simple lab equipment, very I would say primitive tool, but really useful. It's a good demonstration tool. Alright, so these are the topics I want to discuss in this video. The next one is Coulomb's law. I'm going to make a new video for that, and I will make it available to you soon. But for the time being, this is all for now. Alright, thank you everybody.